All right, as promised, here are the big ones. An Euler path, again, Euler, is a path that uses all of the edges of the original graph. An Euler circuit is a circuit that uses all the edges of the original graph. You could also say an Euler circuit is an Euler path that starts and ends at the same vertex. However you want to define it is totally fine. So when you think Euler, you want to think all edges are being used. Euler means all edges are being used. We actually already had some examples of Euler paths and Euler circuits. So we had these graphs before. Let's try to find some other Euler paths and Euler circuits. There's more than one. In fact, I'm trying to go from memory here. I'm going to get these wrong. So we can do C, C. So that means take the loop. And then we can go to B. And then A, E. B, A, E. That's cool. And then we can say F, C. So F, C. And then E, D. E, D. So that's an Euler circuit, another example of one. Now, there is some tricks going on here. Notice when I went from A to E, I did not go to B. I did not go to D, because if I went to D, I would have been in trouble because I didn't finish all of my edges yet. So please be very careful of that. Notice that DE is a bridge, and you want to basically use bridges last if you can. And I realize in the second drawing, there's a mistake. Bump, bump, bump. Oh, I know what happened. One of my edges didn't copy. Oh, PowerPoint, why you hate me? All right, so I'm going to draw in a new edge. You're going to love it. It's going to be the best edge you've ever seen in your life. Let's see. I'm going to put it right here. So if you would, please make sure that gets drawn in. That probably means it's floating somewhere in a PowerPoint slide. That's so weird. Okay. So for the one on the right, let's find an Euler circuit. I could say, for instance, B, C, F, E. So B, C, F, E. I could then say E to C, C to D. So that's the edge I just created there. D to itself, so take the loop. D to E, E to A, and A to B. So let me label these. That's an Euler circuit. This one over here was an Euler path. The Euler circuits are a little bit easier than Euler paths because for an Euler path, there is something you have to do so that you start and end correctly. If I told you, hey, for the first one, you can use all the edges, and you just picked willy-nilly one of the vertices and started tracing, you may not be able to use all the edges. So if you would, why don't you try it? Why don't you try to redraw that graph and determine if you can use all the edges? There is a trick to it. Also with the second graph, Euler circuits are a little bit easier, as mentioned. However, you have to be careful because you need to make sure in both cases that you use all of the edges. So you don't want to paint yourself into a corner where you have no place to go. So before, if I had gone B to C, C to F, F to E, and then if I said E to A, I'd be in trouble because I wouldn't be able to do the rest of the graph, including the loop on D. So there are rules here on how to do it, which we get to. I think that's the next slide. There it is. It's called Euler's theorem. Now, pause the video. Read all that. I'll wait. So if you have no vertices of odd degree, then you have at least one Euler circuit. If you have two vertices of odd degree, you don't have an Euler circuit, but you will have an Euler path. And if you have four or more vertices of odd degree, then there is neither an Euler circuit nor an Euler path. So remember, odd vertices must come in pairs. In case 1, there's 0. In case 2, there's 2. In case 3, there's 4 or more. So 4, 6, 8, 10. So they must be an even pairing. If you have none, Euler circuit. If you have 2, Euler path. If you have 4 or more, neither. So going back the slide there, oh, I thought I got rid of it. The graph on the left had an Euler path. There is no way to make an Euler circuit for the graph on the left. There's no way to start at C and end at C and use all the edges. Impossible. The graph on the right had an Euler circuit. An Euler circuit is a type of Euler path that happens to start and end at the same place. But as far as using the best answer, Euler circuit would be best because we started and ended at the same place. Okay, so that is Euler's theorem. Very, very important. Now that we have that, actually, let me go back real quick because this part is important. The Euler path must begin at one odd vertex and end at the other. That is how you draw an Euler path. So again, if you just picked willy-nilly, you may not get the right ones. If you go back to our drawing here, notice I started at C and ended at D. What's the vertex? What's the degree of D? 1. And what's the degree of C? 5. So that's why I started at C and ended at D. In the previous video, I started at D and ended at C. If I had started at B, there'd be no way for me to get back to, there'd be no way for me to use all the edges. Completely impossible. Try it if you want to. You'll notice it's the same thing. So Euler circuits, you can start and end anywhere you want to. Euler paths, you must start at one odd and end at the other odd. Okay, that's all good there. Okay, so a warning and a note. So again, Euler paths and circuits rely on finding the degree of the vertex. Remember, odd vertices must come in pairs, and you cannot have a total degree that is odd. In the book, there is this algorithm. I cannot pronounce its name, so I'm going to pronounce it Flu's. Flu's algorithm is a way to find Euler paths and Euler circuits. If you get stuck, please reference it. But again, if you use the tips that I've been mentioning, you should totally be fine. So if you would, please watch the video, Finding Euler Paths and Euler Circuits.